from the ED at the Medicine School, who talked about childhood infectious diseases. And on the 15th of December, Mario Belensonas, an architecture, will talk about the Iowa Farming Corridor. Today, we have a seminar of Michael Celia. Michael is the Theodora Shelton Pitney Professor of Environmental Studies in the Civil and Environmental Engineering Department. Michael got his undergraduate degree at Lafayette College, which is not very far from here, across the river. He got 3 more degrees from Princeton University. We mentioned all of them. It's going to be 3 undergraduate degrees from Princeton. It's a very cool thing. His whole career has been at Princeton, except for 4 years at MIT. We're actually colleagues at MIT for 4 years. And Michael came and left quickly to go back to Princeton. Currently, just publishing only at Princeton University. Michael is a leading environmental. He has written a number of awards, fellow of AS, fellow of HU. But what impresses me the most about Michael is that he's gotten regularly teaching awards, both at MIT and at Princeton. That's a remarkable achievement that not everybody can match. Michael will talk to us today about CO2 sequestration.
Thank you, Francois. I like to think that you followed me to Princeton, actually, is the way it worked out. All right, so good afternoon, everyone. The topic is carbon capture and storage, with a focus on the storage part, and particularly focus on the geological storage part. I want to point out my collaborators here, who have, as always, done essentially all the work. Is that lighting okay? You want more lights?
Very good.
All right. Jan has been a long-time collaborator. He's a mathematician from the University of Bergen. Bo, Ryan, Shinwo are students at the moment. Carl is a research scholar in my group. Mary was a student with me. She's now a postdoc at Stanford. And Stefan is at a place called Alberta Innovates, that's the INN, who is also a long-time collaborator. All right. Just what I'd like to do is to say a few words about CCS. If you don't know what it is, I assume everyone does, but maybe not. Most of the time I'll talk about what would typically be considered conventional places to put the CO2 underground, which are basically reservoirs underground that have high enough porosity and permeability to make them productive in a sort of oil and gas sense. Or we might, if they don't have oil and gas, we might refer to them as deep aquifers, meaning that fluids can move relatively easily. And that has been the location where almost all the work has been done, thinking about injecting CO2 underground. One of the issues that comes up, among others, is the question about leakage. You put a lot of CO2 underground, how much is going to stay there? And what are the possible pathways through which the CO2 might leak back towards the surface or to the surface? And in North America, it turns out that probably the most interesting pathway are old oil and gas wells. And we spent a lot of time trying to figure out if we could make a quantitative estimate of leakage risk along old wells in North America. And that'll be sort of the part of the talk, bullets 3 and 4. And we did a lot of modeling. I like to do models, to do computational things. But in this case, we had essentially no data about old abandoned wells. So we wound up having to do or get involved with a couple of different measurement programs. And I'll try to explain those. And then with the models and the measurements, I'll try to put those two together to come to some conclusion about leakage along old wells. In the last part, I want to say a few words about an idea that has come up just in the last couple of years. And that is, does it make sense to think about injecting CO2 into depleted shale-gas reservoirs? And, well, I'll say a few words about how we're approaching that problem. All right, the motivation, you all know this curve. Atmospheric CO2 concentration is going up. It's well above any reasonable background level. This year is special because we are passing through 400 parts per million. Students in the room, I'm sure, will see 450 and maybe 500. Those of us who are older, hopefully we see 450 at the time. I don't mean that 450 is a good number. It just means we should be around for it. Anyway, this is the sort of thing that we think about. The second motivation is this. I don't want to dwell on this too much. This comes from an IEA publication. And if you just look at the left here, it's a projection out from today for the next couple of decades. The amount of CO2 to be captured and stored in million tons of CO2 per year. All right, so you see a goal for 2020 is something maybe, what, 100 or 200 million tons of CO2 per year being put away. But you see this ramps up quickly. So within 15 years, we're supposed to be above 2 gigatons, according to this particular roadmap. Eventually, by mid-century, we'll go up to something like 8 gigatons. If you look at more recent IPCC publications, for some of the things they look at, they're even more bullish on CCS and give even higher numbers than these. Okay? If you put this in the context of the Pacala-Sokolov wedges, you're talking about something like 2 wedges to be achieved by mid-century. Okay? It's an enormously tall order. It's unlikely we'll get there. But anyway, as background, in almost all projections of a decarbonized world, CCS plays some significant role. And our interest has been to ask this question. If you were to actually have a very large-scale CCS activity, are there unintended consequences, or are there environmental implications that we should be thinking about now, perhaps to reorient the conversation a little bit? All right, that's the motivation. The idea, you probably know, is that we want to continue to power certain processes with fossil fuels, but we also want to address the carbon footprint. CCS is the only technology that exists that allows you to do both. To continue to use fossil fuels and to do something about carbon. And the idea is that you would have, in one way or another, a capture facility that would capture CO2 from large stationary sources and put it somewhere in the atmosphere. And the things that have been explored in some detail, deep saline aquifers, unminable coal, and various forms of oil and gas reservoirs with or without enhanced oil recovery. And that's the basic idea. You can still use fossil fuels. One way or another, you capture the CO2, you then put it back underground, in some sense, where you took it from. Here are some estimates that are the most recent from the U.S. Department of Energy. And these are for U.S. storage capacity, estimated in various ways. Here's the unminable coal, depleted oil and gas, and these deep saline aquifers. You see the biggest number by far is in these deep saline aquifers. And any reasonable projection that has CCS coming online in a large way will have to involve injection into these deep saline aquifers. And that's really where we focus most of our work in terms of what we looked at. By the way, for context, globally we're emitting something like 40 gigatons of CO2 a year right now. And you can see how these relate just from the U.S. perspective in terms of storage. There's a lot of capacity to put CO2 underground. All right. I will mention a little bit at the end that the corollary to capacity is the rate at which you can access the capacity. Right? It's not enough to have enough storage capacity. You need to be able to put away all the output that somebody gives you in this year. All right? So it's the rate at which you can access it that's also important. And that's a big difference between conventional and unconventional reservoirs. Both of them have enormous capacity. Only one of them really has reasonable injection rates. All right, let me give you an example just to sort of orient ourselves. Here's a map you see of Norway and the rest of Scandinavia. On here with the dots are various locations that are relevant for CCS activities. I will only mention 2. The first is Snøhvit, which is up here off the northern part of Norway, where the Norwegian oil company Statoil has an ongoing injection operation into formations that are underneath the North Sea from one of their offshore platforms, and it's injecting about 500,000 tons a year. The one that's much better known is this Sleipner injection, which injects close to 1 million tons a year, and we can look at it a little bit more closely. It's been in operation since 1996, and it injects into a formation that's called the Utsira Formation. Turns out this is a formation with essentially unconsolidated sands of high porosity, high permeability, and very high injectivity, and very high storage capacity. Estimates are that you could store essentially all the emissions from Europe in this formation over some number of decades. Okay, so it's one of these sweet spots where you can think about doing injection. Statoil, at the moment, has this offshore platform. They produce gas. The gas has a CO2 content that's too high to send the gas to market. So they have to separate the CO2 from the natural gas, from the methane. And what they do is they do the separation on the platform, and they then, so that the injection comes from the Sleipner field, hence the name of the platform. They then take the CO2, instead of venting it to the atmosphere, they send it back underground into this Utsira Formation here. All right? The Utsira Formation has two important properties. One, it's very permeable and very porous, so it's easy to push the fluid in. And the second is it's overlain by very good cap rock, which is a rock of very low permeability. When you inject the CO2, it has a lower density than the background brine, so there's a buoyant force that moves it up, and you always need a good cap rock sitting on top of your injection formation. When you have those two things, you win the game, and you have typically a successful operation. All right, so a little bit about Sleipner. They inject close to 1 million tons a year since the mid-90s. They will say that they were driven by environmental concerns, at least partly, but my guess is that they were really driven by the fact that in the mid-90s in Norway, they had already implemented a tax that said any offshore emission will be taxed at about $35 a ton of CO2. And Statoil realized that they could inject for something like $10 a ton. So instead of spending 35 to emit it to the atmosphere, they spend 10 and they push it back underground. All right, so the obvious thing, taxation works to change behaviors. And this has now been going on for close to 20 years. It's extensively studied using seismics and other sorts of things to find where the CO2 is going. According to the Global CCS Institute, this is one of what they consider to be 14 large-scale projects that are currently operational, with another 8 under construction. Now, if just as a side note, if I take these 22 projects that they reference and I add up the maximum potential capacity for capture of these 22 projects, it comes out to about 40 million tons a year. And if you remember the projection, and given that the length of construction required, that's not a bad estimate, I think, for 2020. So if you go back to one of the first slides showing the growth curve, where we're supposed to be at about 200 million or something like that, okay? By 2020, we're probably going to be at 40 to 50 as kind of an upper limit. So one of the things that we'll see is that we're well below projections, and whether that changes or not remains to be seen. All right, that's where we're at. So you can ask many questions about this particular activity. How far does the CO2 move while you're injecting, and maybe once you finish injecting? I would say equally important. When you do the injection, of course, the fluid goes in because you push it, meaning you put a high pressure on it. And that pressure pulse will go out into your formation and maybe in other places. And it turns out that the pressure pulse will go out much further than the CO2 does. And in the US, EPA has written regulations for this particular technology where the spatial extent of the pressure plume turns out to be important in defining what they call the area of review. So we really need to also know something about where the pressure is going, not just where the CO2 is going. What I'll focus on in this, we've done various kinds of studies of all 4 of these questions. Third one has to do with leakage. I'll get back to that in a minute. And the fourth one generally is, okay, if you look out over longer time horizons, what happens to the CO2? All of these are interesting questions, but I want to focus on this question, which is, are we going to have any significant leakage? And can we say something quantitative about it? All right, so now we go back to another cartoon sketch. And here the idea is that you do an injection into a formation, you've got a good cap rock, everybody's happy, but there may be localized pathways that allow for faults, fracture zones, or the thing that I will be thinking about for the next sort of 15 minutes are old wells. And why would I think about old wells? Here's a map global map. This came from IPCC, a special report on CCS. It shows locations around the globe that are good places to think about doing CCS. And if you focus on North America, you see that the areas are basically the mid-continent sedimentary basins in North America. You superpose this image with the next one from the same report. This is the spatial density of oil and gas wells. The darkest reds, if you read the scale, are 2 to 6 wells per square kilometer. Okay, then the next one is half a well to 2 wells per square kilometer, etc. And you see that in these places that are really good for CCS, they also happen to be historically quite good for oil and gas production. So we wind up with some number of millions of old wells in North America. So I'll show you an example. If we walk into the province of Alberta, right, the energy producing province in Canada, the city of Edmonton, which is the provincial capital, if you go to the southwest, in this region here, there are 4 existing coal-fired power plants collectively emitting around 30 million tons of CO2 a year. So early on, we thought this might be a good place to think about doing a CCS operation if someone were so inclined. So we did a lot of work on this sort of yellow outlined area, which turns out to be 50 kilometers by 50 kilometers on size. Among other things, if you look at this, this is the 50 by 50 here. Each of these is called a township. Each of these dots is an existing oil or gas well. And everybody at Princeton is really very fast in terms of doing things. I'm sure you can quickly add these up and you get something like 1,200 wells. So I have 1,200 wells in an area that's 2,500 square kilometers. That's about half a well per square kilometer, which was the low end of the second darkest red in my map. So these don't appear to be unusual in terms of their spatial density. But that made us think differently about how we might imagine an injection scenario. So instead of having a nice cap rock here that will just block everything, in fact, I probably have a very good cap rock, but I've drilled a bunch of holes in the cap rock, and the purpose of these holes is to allow fluid to move easily from the deep part to the surface. Right? If you want to produce fluids, that's what you do. So the question was, is it possible that either the injected CO2 or some of the brine, or both, might leak along these wells? If so, how much? What's the role of intervening permeable layers in terms of secondary plumes? How much gets into the shallow zone, and eventually how much might get back to the atmosphere? That became our kind of set of questions. The shallow zone in this case is important because all the rules written by EPA are written under something called the Underground Injection Control Program, UIC, which is created as part of the Safe Drinking Water Act. So the motivation for the regulations for CCS written in the US are underground drinking water protection. So it's all about potable aquifers and their protection. That's why the shallow zone is important. All right. To do this, I had to go learn something about how oil wells are created and what kind of cements they use, and think about all kinds of possible small-scale pathways and how we're going to deal with them. It turns out that if you inject CO2 into a brine-filled formation, some of the CO2 will dissolve and lower the pH, and that lowered pH aqueous solution can be fairly aggressive to typical well cements. So we had a sort of ongoing experimental program here with one of our students, Andrew Duguid, along with George Shearer, to try to understand cement behavior. I was more interested in asking the broader question, is how am I supposed to deal with this thing? I've got very large domains, very small, important pathways, and at the time, I had essentially no information about what kind of characteristics abandoned wells had. Right? Imagine you have a well that you've abandoned. Do you want to go back out to the abandoned well and tell me if it's leaking? Probably not, because the only thing that can happen is bad. Right? Either it's okay, in which case there's no change, or there's a problem, in which case you have to fix it. So we talked to a lot of various people in the industry. Sometimes we got agreements that we would get information, but at the end of the day, we never really got information. So that made me think about the fact that I'm going to be doing lots of Monte Carlo simulations, and lots of tens of thousands of simulations of this kind of system. It turns out that at the time, if I just pulled it off the shelf computer simulator, I couldn't do one simulation of the kind of problem I showed you in Alberta. Computationally, it just wasn't possible. So we spent a lot of time trying to figure out how we could put models together of the system. A little bit of information. If you look at this phase diagram for CO2, just to give you a sense of what's going on, the critical point is here at about 31 degrees C and about 7.5 MPa. And at typical pressure and temperature gradients, you will pass the critical point at about 800 meters depth. So almost everybody talks about injecting below 800 meters because you want the fluid to be in a supercritical state because there's a much higher density, 500, 600 kilograms per cubic meter, as opposed to a gas density. So you get this density, but you still have a density difference with the background brine of about 500 kilograms per cubic meter. So very strong buoyant drive. It's a little bit soluble, meaning it will stay as a separate fluid phase, but a little bit will dissolve. That leads to pH changes, etc. Viscosity I'm not going to worry about at all. And if you inject dry CO2, some of the H2O is going to evaporate, create wet CO2. That can be corrosive to pipes. I'm not going to worry about this either. We can talk about it. So you wind up with sort of a multi-phase, multi-fluid phase, multi-component system that you need to think about in these porous media. The geochemistry might be important. For example, I already said something about well cements, but other reactions could be driven. Geomechanics can be important because if we want to get anywhere close to the amount we need to inject, I have to inject at as high a pressure as I can get away with. All right, and so the mechanics may be important. Non-isothermal effects can be important, etc. So the system can get fairly complicated if you let it. We took a slightly different approach, which was we wanted to ask ourselves, how simple can we make the system to get something useful? All right, and that, at the end of the day, led us to a sort of semi-analytical solution, which I like a lot. And we built it up with a lot of pieces. There's a piece that we published in Journal of Mechanics, ES&T, various things. All of these are pieces of the problem, where I have an injection, I have a bunch of leaky wells, potentially leaky wells, and a bunch of different formations here in the vertical stack. And you can write a bunch of equations, and our interest was in solving this system efficiently so that I could explore parameter spaces for things like effective permeability of a leaky well, for which I had no information, and therefore I had to think about it in some very broad stochastic way. The upshot is number 4 here, which is that by having a bunch of clever people I work with, we can now solve the Alberta problem I showed you with 10 layers in the vertical and 1,200 wells and etc. in about 5 minutes on my laptop. We can get where the CO2 goes, what the pressure pulse looks like, where the brine is leaking, how much CO2 is leaking, all the sorts of things we're interested in. And that gives me lots of flexibility. So, for example, I can go back to this. This is the map. These are the maps we saw before. All right. If you project them on the vertical, they look like this. I'll show you results for injection into a formation called the Nisku formation. It turns out to be a good formation for various reasons. So, for example, in this case, we run 1,000 realizations where I, in my own mind, make up what I think might be a reasonable probability distribution for permeability of leaky wells. All right? You can tell me it's completely crazy. It might be crazy, but that's the best I could do. And then I said, okay, let's think about all the different parameters I could modify. But here, 1,000 realization for a particular case. This is with the different correlation structures. But this is the log of the fraction of mass of injected CO2 that leaks into the shallow zones after 50 years of injection. And for example, this distribution tells you that on average it's well below 1%, and even at 95% sort of confidence it's well below 1% for this particular case. All right, so we did hundreds of thousands of simulations. And my original idea was, at least we had a project with the EPA, at least I might be able to say something like, if you want to be convinced that a particular field is okay, these are the kind of statistics that the operator who's giving you an application should look like. Right? And at that point, it's sort of up to them to argue that the statistics of these wells are okay. At the same time, we were really interested in whether or not we could get some actual data. So the first project that we were involved with was jointly with BP, who has sponsored much of this work through the CMI, and also Schlumberger, going out into the field with this kind of a rig. It's a Schlumberger drilling rig, and re-entering old wells. All right, and in this case, the guys from Schlumberger would go down the well, whatever, a few kilometers sometimes, and they would turn their tool sideways and they'd start drilling sideways. And they could take a core, a side drilled core, that would, for example, capture the casing itself, the cement that sits outside the casing, and then the rock that's beyond the cement. You can take it up, you can do experiments on it, you can do all sorts of things, all right? Really interesting information, but not really all that useful for what I was interested in. I was much more interested in pathways that might be, for example, annular flow between these pairs. And that's hard to see when you do this sidewall work. So they also were kind enough to do larger scale testing based on pressure transients that gave us other kinds of information. So for example, without going into the details, the industry calls this a vertical interference test, VIT. So the well drillers went out and actually did these experiments, sent us the data, and one of my students at the time was able to do an inverse modeling. And in this case, for a section of well that was about 3 meters, we got an effective permeability outside of casing in the region between the rock and the casing, meaning cement and anything else that was there, of about 170 millibars. Okay, what this particular value of permeability. Really cool data. We were very excited about this. But it only gave us, at the end of the day, up till now, in the last like 8 years, about a dozen data points. All right. So we also, for various reasons, have done some other measurements in old wells. This is a photo taken, I don't know, last year sometime. This is my former student, Mary Kang, back when she was still a student, and my other former student, Alana Miller, back when she was still a student. And they're out measuring methane fluxes from old wells in Pennsylvania. There's a well inside this thing here. Okay, you go to Home Depot and build this thing yourself. You just get a little bit of plastic, you put it over the well, and then you have a sampling port, and you measure concentration versus time, and that tells you the flux rate that's coming into the chamber from the well. All right? It's really great. The wells in Pennsylvania are really interesting. Some of them are really bad in terms of what shape they're in. Most of them don't exist on any databases. Makes for a very challenging and interesting project. And at the end of the day, our primary interest in this project, which I'm not going to say anything about today, was done along with Denise and with TC and Peter Jaffe's group and Mark Zondo's group, was trying to figure out how much methane was coming out of these wells. And it turns out to be not insignificant and an interesting story. As a corollary to this, if you're willing to make some simplifying assumptions, it turns out that we can also use these measurements to estimate the effective permeabilities of these leaky wells in Pennsylvania. All right, and this is something that just came out a little bit ago. And we did this for 30-some wells. And here's a plot of each of the wells with sort of error bars on it, etc. The axis here is in millidarcies again. And what you see here is that the range is from about 100 millidarcies to something well below that. All right, so that's what we see. Let me get rid of this because I have more things showing up. If I take this data, it plots here, and if I take all the rest of the data we got from these re-entering old wells, it's the blue dots on the vertical axis. And if I take a different analysis that was done with a different data set by a group at the University of Texas, Steve Bryant's group, they saw that range of values. All right, so literally just in the last year or year and a half, we suddenly have these data sets from which we can infer a range of values for old and, in the case of Pennsylvania, some of which are quite leaky wells. All right, and this is what we get. And if I take these values and put them back into all of these, hundreds of thousands of simulations we did, for the injection I showed you in Alberta, in that Nisku formation, it turns out that our expectation is that the leakage will be well less than 1% of the amount that we inject after 50 years, right, which we think is a good result. So for me, it's a little bit surprising that the rate is that low, but that's what comes out. And I'll say a few words about that as we go. So that's the first part. We're interested in leakage. After lots of work to put new models together and get a whole bunch of new data, we're able to come to some tentative statement about a quantitative leakage estimate, which for me says leaky wells are unlikely to be showstoppers for CCS. Right, that's kind of the figure of this. All right. That's all I wanted to say about the conventional reservoirs. I'll be happy to answer other questions and other topics, which we find. But I wanted to say a few words about these unconventional reservoirs. Unconventional means that typically the permeability is not very high, and you need to stimulate the formation to get any fluid out of it. It means you need to fracture it. All right. So there were studies done that came out within the last 5 years or so that basically say, hey, if I look at something like the Marcellus Shale, right, in Pennsylvania, mostly in Pennsylvania, and I just look at the estimated capacity in terms of space available to put CO2, it's a very big number. 50 gigatons or something like that, right? It's a big number. So therefore, this looks like a good idea, all right? So we were interested in whether or not we thought that was a good idea. So we've looked at some data and done some modeling for the Barnett Shale down here in Texas, one of the earliest formations that was produced using these horizontal wells with hydraulic fracturing, and then the Marcellus. And in the Marcellus, it turns out the characteristics of the formation are sufficiently different that we break it up into the northeastern PA region and the southwestern PA region, so two different regions of the Marcellus. All right. Most of you probably know that when you produce gas out of these formations, you drill vertically and then you can deviate the well, you start going horizontally, and when the well is in place, you will then hack off sections and perforate the piping, etc., and then hit the formation with a very high pressure pulse of water that creates these fractures that typically orient more or less vertically. All right? And you decide on some spacing, whatever it happens to be. Spacing is sort of changing with time, but you create these fractures by pushing in this water, and then you allow the system to typically shut in for a while, and then you start producing gas. All right. A side comment, by the way, some of you may know that one of the things that go on here, I don't know if it's controversial, but let's say one of the things that is focused on is the fact that during some of the early flowback, you get methane that comes back up the well that is just vented into the air. All right, and there's been a lot of debate and a lot of measurement programs about how much of that methane, fugitive methane, goes into the atmosphere and what its impact is and those sorts of things. Just as a context, if we go back and just look at what other people have done in terms of estimating the amount of methane going into the atmosphere from these producing wells, for which a lot of work has been done, and we compare that to our estimates of how much methane is coming out of these old abandoned wells that nobody really likes to think about, the numbers are about the same. For me, the difference is that these wells, these producing wells, are relatively easy to fix because there's an operator who can be regulated and whose behavior can be taken care of. The old wells sitting in the backwoods of Pennsylvania are much more difficult to remediate. But anyway, just as a context. All right, lots of interesting questions here about fracking fluid, where does it go, all sorts of things like that. We were interested in the simple question, which is, I go produce this well, right? I first put in the fracking fluid to make the fracture. I then start producing the gas for some number of years. When I'm finished, does it ever make sense to come back and push CO2 into this thing for the purpose of carbon storage? It turns out that those of you, a lot of you know more geology than I do, I'm sure. And these shales are really complicated. People have done lots of studies looking at the small-scale structure and the nanometer-sized pores and how complicated the fluid mechanics are in all these pores and how the structure is really complex. And yet it turns out, this is a paper from last year, it's a different group at UT Austin, Pet's group, where they looked at the Barnett formation in Texas. And they observed that for for essentially all the wells, 8,000 some wells, that what they observed is a kind of universality that at early time, the production rate went as the square root of T, and at late time, it went as e to the minus T. And anybody who knows solutions of simple diffusion equations will tell you, that's exactly the behavior of a straightforward diffusion equation. Meaning, simple Darcy flow seems to do a good job of predicting the gas flow, which was quite interesting. At the time, I actually had a project joint with Eric Larson and Lynn Liu. And my job was to make an estimate of how much CO2, I'm sure Bob was involved as well, how much CO2 we could put into to these shales. And at the time, I had no idea how I was going to do it, because it all looked really complicated to me. And then, of course, I realized that, okay, if this is true, then I can make a leap and say it's probably also true if I think about putting CO2 in a two-component mixture instead of just looking at methane. Anyway, so the idea was that the system seems to behave, at least from a modeling perspective, as simple one-dimensional, Darcy flow. So you can write these if you're interested in equations. I put a few equations here in one dimension because these are nice and easy. So this becomes sort of the simple governing equation, second order derivative in space, first order in time. You put sorption in and desorption and all those sorts of things, but it still works perfectly fine. And so we did this looking not only at production rates in the Barnett, but also in the Marcellus. And we get extremely good fits to all the data we've looked at in these formations. So we looked at about 9,000 wells here, 1,500 wells there. The parameters we get all look reasonable for these kinds of shales in terms of looking at the macroscopic properties that are reported in the literature. So we said, okay, let's make a leap and say, I'll assume a nice simple one-dimensional equation set like this will work fine. Now I have both CO2 and methane. I've got competitive sorption and lots of other things that you have to think about, but structurally, the mathematics of it is still straightforward. So we use this to then ask, if we go back to the Barnett or Marcellus, and I say, look, it seems reasonable that when I inject the CO2, of course the pressure is now depleted in the formation because you've been producing, I'm going to allow myself to increase the pressure to inject the CO2 through these major fractures up to the original pressure of the formation. It seems like something a regulator would be okay with. If you do that, then you see these kinds of cumulative amounts injected for, in this case, the Barnett down at the bottom, and then the two Marcellus here. Into any one of these horizontal wells, you can get a fraction of 1,000,000 tons at the end of its lifetime. All right, and it turns out that for a single coal-fired power plant, that means that in the Barnett you need about 700 of these wells and sort of 200 to 300 in Pennsylvania. The reason is that the permeability here is so low that you just can't get much in terms of rate. So we asked that if I look at Pennsylvania, identify the major stationary sources, which are the triangles, scaled by emission rates, and we just ask this question. If I take these 5 large sources, which are coal-fired power plants in southwest Pennsylvania, how many of these shale wells will I need to inject the output from these power plants for, I think it was a 40-year time horizon. And it turns out that if you say, the algorithm I'll use is I will choose the nearest wells. All of these dots are either existing shale gas wells or wells that have been permitted but not yet they have been permitted, so we took both. You need about 5,600 wells to do that. On the other hand, northeast Pennsylvania turns out to be a better formation in terms of its properties, so you only need about 3,500 wells. We then said, okay, these seem like unreasonably large numbers to us, but you know, my intuition might be wrong. So we're in the process now of asking ourselves, could we put any reasonable pipelines in place to connect up these 6,000 or 3,000 or whatever number of wells back to these sources? And if you want to do it in the southwest, you know, you need about 6,000 kilometers of pipe. If you're willing to run a pipeline up to the northeast, then in fact you wind up with a smaller amount. Now, is this interesting or not? The interesting part for me is the context, which is in the US, you remember that out in the mid-continent is where all of the sort of sweet spots are for conventional reservoirs for injection. And in particular, in the Illinois basin, the Mount Simon Formation is in some sense like the Utsira Formation off of Norway, which is that it can take a lot of CO2 okay, in this sort of thick, permeable, conventional formation. So in this case, we can think about taking these sources here, running a pipeline along appropriate right-of-ways and all sorts of things like that. And you need relatively few wells to do the injection out here, as opposed to 1,000 or 6,000, whatever the number is, you need a handful of wells. The advantage of this, of course, is that you can think about other sources along the way that would contribute to the cost of the pipeline and use the pipeline to come out here into this conventional reservoir. So at the moment, we're in the process of working out the economics of whether or not it will ever make sense to do large-scale injection into these depleted shale gas reservoirs. Intuitively, it seems to me the answer is no, but every time I say that, there's somebody who says, oh, no, I disagree. It seems reasonable to me. All right, so the only way that I could answer that criticism, that question, I guess, that other opinion, is to say, at the end of the day, no, it costs a lot more to do it, but so that's what we're in the process of doing right now. All right. So, conclusions. I'll remind you that CCS is the only technology available that allows for both carbon mitigation and continued use of fossil fuels. You don't use CCS, then you get to choose between these two. Everybody would like to simply decide to stop using fossil fuels. That seems unlikely and an unreasonable assumption at the moment. We've done a lot of simplified models. We like to put them in multi-scale context and do lots of things like that because we think it can help us answer practical questions. One of them is about leakage along old wells, which from our initial analysis using the recent data that we have generated indicates that the amount of leakage seems to be relatively minimal. I'd say being politically not difficult here, I will consider CCS into shale gas formations to be logistically challenging. You just need a lot of pipes going to a lot of wells. There are regulatory issues associated with it. There are lots of things that I think become difficult to think about large-scale injection into these depleted shale gas formations. If you have small local sources, then in fact it may make sense. And at the end of the day, it's also the case that CCS deployment at the large scale basically has yet to happen. There are around 20 projects. Most of the largest fraction of the existing, 22 projects are of the kind that are like the Sleipner gas production field, which is that you have a gas separation facility where you're producing essentially a pure stream of CO2. It's easy to capture and not too expensive to inject. The hard part is that most of the emissions come from power plants where the source of the CO2 is dilute and the cost of capture is much higher. So in some sense, the cost of capture, I think, has largely been the reason for this lagging in terms of deployment. All right, that's it. I tried to leave 5 minutes for questions, and I'm happy to take any questions that you have. Thank you.
I'm wondering what the ratio is of the volume of CO2 you're injecting to the volume of solid water in the aquifer.
Yeah,
And what the consequences are.
Yeah, the consequences are an interesting question. The volumes tend to be relatively small. If you look at the footprint of the CO2, it tends to be relative to the scale of a typical formation globally. As I said, the pressure pulse goes out a lot more. But certainty you can say that the CO2 will remain in the formation, and that the brine will remain in the formation as well. And that's really where we've been focusing our attention. The second one, which I haven't said anything about, has to do with geomechanics, the possibility of reduced seismicity, and whether or not you have any faults in the neighborhood, which you would presumably not choose a site that would be potentially seismically active, but that is certainly another discussion. Yeah.
You talk about slow permeability leaks. Is there any risk of a catastrophic leak which might cause such inconvenience as say suffocating a town?
Yeah, that's a good question. Of course, people think about Lake Nyos and they worry about that. There's been really interesting work done by a colleague out at Lawrence Berkeley National Lab, where he tried very hard to come up with scenarios that would give catastrophic leakage, and was unable to do it. In large part, because the nonlinearities in the system tend to feed back to limit the sort of runaway behavior that you're talking about. All right? If you well, I'm happy to point you to that work, but I have not seen any credible scenario associated. Of course, if you were to inject under a large body of water that was next to a town that could potentially accumulate, like you could create a Lake Nyos, okay, but presumably you wouldn't do that. At some level, I guess you could come up with a scenario, but for the kinds of things I'm talking about, leakage along wells, leakage along faults, and those sorts of things, so far, no one has been able to come up with a scenario where you see that kind of behavior. Yeah.
What do local surface concentrations?
Sorry, I can't hear you.
What do local surface concentrations look like when you would have a leaky well or some other leakage, and what kind of ecological impact might that have?
Yeah, all of these, I think, wind up dispersing very quickly. And these leaky methane wells, all right, oftentimes you can smell them because you get other things in addition to methane coming out. But if you just walk along with a handheld sensor and you try to identify, a hotspot of concentration, if you do, it will be very localized around the well. You don't tend to see, large-scale impacts. Maybe there are examples of natural releases where you can see those things, at Mammoth Mountain or things like that, right? But that's like 500,000 or 1 million tons a year that's leaking out, all right? And here we're talking about a very small fraction of that. So yeah, if you get 1 million tons leaking out, then you can have impacts on vegetation for sure. But that's a completely different order of magnitude. Yeah.
Do the oil companies have the holes that are measuring?
Yeah, sure. Of course, the requirements are that you need to plug the well, and usually that means that inside the casing, you have to put some specified minimal length of cement, and at different intervals along the well. All right. So, yes, the regulations say you should do that. There are two things about that. One is that in a place like Pennsylvania, where the first commercial oil well was drilled in 1859, and they've gone through various oil and gas booms in the last 150 years. As you saw, maybe if you noticed the photos of some of the wells in Pennsylvania, for all the wells we measure, it's very difficult for us to determine with certainty if it's been plugged. Okay.
What about the sideways?
So in any event, okay, so I won't get too carried away here. Right, so the regulations say that it should be plugged. The fact is that the industry is old enough that there are certainly wells that exist that are not plugged, all right? But probably not very many, if at all, recent wells that would not be plugged. Right? Now, side holes. We spend a lot of time worrying about leakage pathways outside the casing. okay, where it's much more difficult to get to. You can always, in some sense, you can relatively easily plug the inside of the well, but fixing the outside of the well is much more difficult. So in that sense, yeah, when you perforate the well, when the well is put in place, okay, during part of the construction, they do what's called a cement job, which is that they will squeeze cement up between the casing and the rock. Okay, so for at least some portions of the well, there's supposed to be competent cement that blocks the pathways, the flow pathways outside the casing, between the casing and the rock. We were interested in characterizing that cement because that was what we're most interested in. But there are possibilities of flow outside of the casing and inside the casing. Plugging takes care of the flow inside the casing, and the original construction of the well is supposed to take care of the flow outside the casing. The extent to which either of those is effective becomes sort of what gives different values of permeability of the well. Bob?
A lot of areas in the world where CCS is likely to be needed don't have hydrocarbon-bearing formations, like China. And I'm wondering if there has been work comparable to your work in these hydrocarbon-intensive reservoirs on the leakage potential through fractures and whatnot. And if there hasn't been such extensive work, what would you care to speculate as to what it would be?
Yeah, so
easier than what?
So you're asking me about formations that have been produced, oil and gas.
Well, that's what you worked on. I'm talking about other parts of the world.
Okay, I see. Okay.
That are not hydrocarbon bearing.
Yeah, yeah.
And what has there been significant leakage research done for such reservoirs? Not necessarily in China, but just where you don't have hydrocarbons, or if not, can you speculate as to how much worse or better it would be than what you have for these hydrocarbons?
Yeah, so the trade-off is this, that if you have an area that has not been produced, then you know you have not put any holes in the cap rock. That's a good thing. The downside is that you also probably have very little information about it because no one has had any particular reason to go look at it. So you walk in with a very little amount of a priori information. And that means that your initial predictions are going to be highly uncertain. Okay, so then the interesting question is, how much site characterization do you need to do in order to have enough confidence to move forward? Right? Because in an oil reservoir, if you have, in some sense, you wind up producing like crazy. All right, typically fill in. You get a lot of information, so that by the end of the life of a reservoir, you know a lot of detail about the formation. Okay, I would say you don't need to know nearly that much detail about the CO2. You just need to know it's going to stay in place. It doesn't really matter if it goes a little bit further here or a little bit further there. Right? The details of the architecture don't really matter, whereas for oil production, the details of the architecture do matter. All right. So I don't think there's an obvious answer to the question of how much site characterization you need to do. I would say that in some of the early projects, I think maybe the operators have been a little bit surprised at the cost of what they have to do, but I think that remains to be determined. Yeah. Yeah, so the answer is the question is, are you also concerned, or are others also concerned about the possibility of leakage outside of casing at the injection well? And I guess the answer is that I have a sort of a bias that says that we should know enough at this point to be able to make sure the injection well is behaving properly. If we can't do that, then we have a problem. All right. That said, it's certainly. I mean, there are companies like I'm sure Schlumberger and I know Halliburton have special cements that are specifically resistant to CO2 corrosion of the kind I showed you. Right. So So they have different additives they will put in to make the cements appropriate for CO2 wells. All right, so those kinds of things, I think, wind up giving a reasonable confidence that you should be able to design an injection well. So I have not myself looked at leakage along injection wells. It's also the case that during the injection, of course, there are lots of things you can measure and test to make sure the well is behaving properly. Okay, those tend to be done as well. Yeah?
What is the ratio of CO2 equivalents taken out of these wells compared to how much you can store of it?
Out of these wells.
So the fracking wells, especially. So if you had 5,000 wells to store the equivalent of one coal.
Well, the equivalent of the 4 large coal-fired power plants. So
Yeah.
a few hundred for one coal-fired plant, yeah.
Yeah. So if you do that, how much have you taken out when you actually?
Talking about how much methane have you taken out?
Yeah, when you did the fracking, when you did the gas extraction.
Yeah, I would say that you could imagine on a volume basis is probably similar.
Okay, but that it has much higher CO2 equivalents.
Yeah, but presumably you're going to burn the gas, and whether you put the CO2 in or not, you're still going to produce the methane. Right now, they're producing the methane and not putting any CO2 back into the formula.
Yeah.
Okay, so it's not a question of. You can ask the same question about which I didn't get into, but most of the projects, most of these 22 projects, at least most of the large ones, and there are 3 of those that are associated with power plants. All the rest of them are other industrial streams. All right, and all 3 of the power plants will use the captured CO2 for enhanced oil recovery. So then you can ask yourself, okay, should I get credit for that because I'm putting the CO2 under to produce more hydrocarbon to burn to produce more CO2, right? And so the answer is, if you were going to produce that remaining hydrocarbon anyway with a different method, okay, then you should get credit for putting the CO2 in. But if it were otherwise going to stay underground, okay, then in fact you get it sort of you sort of balance yourself out in some sense. But I want to be clear that I think that the EOR part turns out to be important, not because of the absolute volume of CO2 that gets put away, but because it allows capture technologies to be further developed and the cost reduced. Okay, that's really important. Yeah.
Well, I think this lady was first.
Okay.
I just am curious, and maybe because it's a different subject matter, why regenerative agriculture isn't part of the CCS dialogue on.
Yeah.
Because there is enough science and land restoration partners, they say now, to draw down 100 megatons of carbon per year.
Sure. That is part of the broader conversation. It's just, that's not what I work on. So, that's what I say. Yes?
Well, as you pointed out, most of the operations where they're doing this, the CO2 is produced as a result of, say, gas extraction, which is contaminated with CO2. You've got to suck it out anyway.
Yep.
Extracting the CO2 from the exhaust port of a powerhouse obviously is a thermodynamic uphill operation. If, for instance, Duck Island were to go to full CO2 capture and run for a week, would there be enough energy left over to wind your watch? I'm being sarcastic. What fraction of the energy?
So the energy penalty is something like 25 or 30% with current technology.
Okay.
Right. So and that's where the major cost comes in, and most of the cost is because you have to pay for the energy to run the extra chemical engineering plant to take the CO2 out. All right. Interestingly enough, the first power plant with capture that has come online is in the process of coming online right now. It's up in Saskatchewan, a place called Boundary Dam Power Plant. And the interesting thing I read about it is that the engineers who designed this plant, after doing it once, have now said that they're quite sure that if they were to do it a second time, they could at least reduce the cost by 20 to 30%. Okay, so the fact is that this first of a kind versus nth of a kind argument, I think, is relevant, and that these early costs are high. But the idea would be that presumably the cost will come down in the way that these guys have said. Yeah.
Have there been any suggestions to use abandoned mines for CO2 storage?
Like abandoned coal mines? What?
Well, what I have in mind is there was a disastrous event in Durango, Colorado, you know, the toxic material from an abandoned mine was released into the water stream.
Yeah.
And with that, basically getting at a question about abandoned mines, whether there have been any suggestions to make use of them for any purpose.
Not that I'm aware of. There has been some discussion about storage in salt zones, but I haven't seen anything about mines. The only thing that we do is we know in Pennsylvania that if you have a well that is drilled in what's identified as coal country, then when you do an abandonment, somebody asked me about abandoning and plugging, then you have to take special precautions because of coal and the presence of methane. But otherwise, yeah, otherwise I don't really have anything else to say about it.
Right. More conversation, one on one.